Okay, so I'm going to be talking about machine learning and game theory like many of the other speakers in the conference. I looked at some of the abstracts and I think I'm going to be in good company. A lot of the other talks are bringing statistical data inference kind of ideas together with game theory, as am I. The one word in my title, which is perhaps distinctive, is had to do with dynamics. So I'm very interested in not just equilibria, but on dynamics of things that converge, both in a game theoretic sense and a learning theoretic sense. I think that Kostas Daskalakis, who's already talked, I think, earlier in the conference, is probably closest to me in that focus on dynamics. So I am coming at this from a machine learning point of view, and I want to kind of emphasize why I believe that game theory and machine learning are natural allies. Now let's be clear on what machine learning is. First of all, I think it's really just statistics with a little bit of dose of computer science. But it's certainly in the last 10 years is focused on a statistical problem, which is pattern recognition. So it's gradient descent based. It's got large numbers of parameters and large sets of data. But pattern recognition is an old terminology from the 60s and 70s. You find patterns in data and essentially you use them to make predictions based on that. And it's become a commodity. So platforms have made it into something that anyone can use and does use. And I won't get into the good and bad about that. Basically, I think it's overall good, but there's a lot of naivete and a lot of lack of error bars and so on and so forth. Nonetheless, it's really only half of the field. There is a decision-making side of the field, which will be more familiar to anyone with a game theory background. And it has to do with high-stakes decisions and explanations for decisions. It has to do with interactions among decisions, including decision makers, and it has to do with market mechanisms. So obviously that's going to be my focus of my talk. I want to say a little bit more about decisions because decision theory is really a joint project of game theorists or economists really and statisticians going back to the 30s. Someone like Wald was both, and von Neumann and so on. So it really is where our fields meet. But let's take now this kind of machine learning perspective on decisions. There is indeed a bit of naivete that if you build a big neural network that has all the world's knowledge in it, whatever that might be, and make perfect predictions, that somehow that's all you need for decision making and for real world applications. This is really not for this audience. This is for the people who promulgate such ideas. But let me say a few things about it anyway. So I'd like to be concrete in this on this slide. So think about a medical example where you're gone to your doctor's office. In the next few years, they will measure hundreds of thousands of things about your body, including maybe they'll sequence your genome. And that 100,000 dimensional feature vector will go into a large predictive system, perhaps a neural net that's been trained on all the world's medical data, just like they're training natural language systems on all the world's dictionaries and encyclopedias these days. So out will come a number for each of the possible diseases you could have. And so perhaps if some number is over 0.7, you're about ready to have a heart attack. And suppose your number is 0.701. Is that thresholding in any sense, meaningful, real world sense, a decision? Answer is definitely not. First of all, you're going to ask for some notion of uncertainty. And it's not going to be just Gaussian error bars around that 0.7. It's going to be about the provenance of the data and the relevance of the data. Is that old data 10 years ago, or is it relevant? Was it about people like me? How is it stratified? How is it collected? What kind of machines were used? And all kinds of issues that we're only dimly aware about, but in a real world decision-making context, we're very aware of. Moreover, you're going to think about counterfactuals. You're going to ask the doctor, well, what if I were to change my diet? Or you're going to add facts that were not known a priori. When I was a kid, I had, laryngitis, or my parents had a disease that I just remembered. Many things will become relevant in the moment that didn't seem relevant in the past. So they actually weren't in that large neural network. It didn't have all the world's relevant knowledge because every decision brings new data to bear, and you're going to want to do new analyses based on those new data that you're thinking about in the moment. So this is what a dialogue about decision-making is about. And this is what a real world decision-making process is always about. You're going to have a dialogue with your doctor. You're going to build trust. You're going to probe. You're going to think. You're going to reason. So neural nets do none of the above, including they don't really have error bars. All right, now it's never just one decision. Today I'm making large numbers of decisions, as I go through my day, and they're interlocking in various ways. There are different timescales, and all of us are doing that. So we're linked across the network. And if you think about the COVID outbreak, it's very much this, that, how the outcome with some person in some city has an effect on treatment of another person in a different city. over stretches of time and space and time. And of course, it's not just over a network, it's over all kinds of time intervals, and it's when there's scarcity and competition. Because making a decision is rarely just simply allocating somebody to something because they want it. It's the trade-offs that are involved when you don't allocate it to other people who may want it as well. Okay, so again, I don't have to emphasize this with you, but in a lot of neural network conferences, this is like, aha, they hadn't thought about all these issues. And here's another point of view, which is very familiar to you. This is kind of the algorithmic game theory perspective. You know, markets are already algorithms and they have intelligence as a market, even if the individual players are not so intelligent. So again, this is obvious to people here, but it's not that common in the AI community. The AI community thinks that every agent has got to be super intelligent, and then the whole thing somehow works. And I think the right perspective is to turn that completely upside down. So we recognize that markets are algorithms that can be adaptive, they can be robust, they can work over very long lifetimes. And then, of course, I want to emphasize that they aren't perfect. They have all kinds of problems. And I think over the next several decades, we're going to have all kinds of new markets involving data collection, data analysis, large scale, large numbers of players, and so on and so forth. Brand new principles are going to need to be to evolve, to be discovered, to work on these kind of markets. So there's going to be tons of new problems at the interface of ML, or statistics really, and game theory. I'm going to mention some of these in my talks. Let me just quickly allude to them. You know, multi-way markets, when you have to learn your preferences by exploration, exploitation. Okay, so we'll talk about that a bit. It's sort of already being worked on, but it's just such an important fact that you don't learn by simply being told the right answer, like in supervised learning. You learn by exploring, and that costs you a little bit, and that goes into the economic equation. Then another dimension is what if we have large-scale multi-way markets where there's millions of agents and each of them have hundreds of millions of options. That's a very typical situation in the real world. You can't write down your preferences a priori, and you can't even do exploration exploitation. So the only way you can go forward is to get recommendations from other players in the market, and you may or may not trust those recommendations, and so on and so forth. So recommendation systems are, just to emphasize that, are a really important thing in the world of applied machine learning. It's up in the top 5. Billion-dollar industries have been created by recommendation systems, but recommendations are very much broken because they don't have an economic model behind them, or a game theoretic model. We'll talk a bit about strategic classification, strategic data gathering, where the data itself is a commodity, where there may be scarcity, where there may be competitive pressures. Auctions in which preferences are learned. There have been several talks about this already. Prices are a way to make things decentralized. And in machine learning, we definitely need to make things decentralized for many, many reasons. So there's still much to do with that interface. And then privacy, risk, computation, trade-offs, bringing all these entities together. I do want to acknowledge of the many people who've already worked on things like this, David Blackwell, who I got to know when I was first at Berkeley. He was a statistician, probabilist, an economist, and a computer scientist. He is rare. So he brought all 3 of the disciplines together. And I kind of like to note that there's a lot of pairwise bringing the disciplines together. So statistics meets economics, that's econometrics, right? Economics meets algorithms, that's algorithmic game theory. Algorithms meet statistics, that's machine learning, right? But it's pretty rare to see all 3 together. And a lot of people in this conference are kind of the heralds of the future in doing this, but David Blackwell was very much already doing it in the 1950s. I'm going to briefly go through 4 recent projects. I've made a selection. Actually, I didn't put as much dynamics in there as I would have liked. If you want to go to my website and look for Langevin dynamics, or the dynamics I mostly am using these days. But these topics are a little more game theoretic in flavor, and so I thought I'd emphasize them in this particular talk. All right, so this is a first kind of thought experiment almost that I did with my students Lydia Liu and Horia Mania at Berkeley, where we brought together my favorite idea from learning, which is the multi-armed bandit, and my favorite idea from microeconomics, which is the matching market. Trying to bring them together in kind of the simplest, purest way, and almost kind of a mathematical thought experiment motivation. So we're more or less motivated by real world problems, and I'll mention that in a moment, but really it's kind of the mathematical tools. So the multi-armed bandit, hopefully you already know what it is. I have an agent who has several options, and they don't know their preferences or utilities for the options a priori. They have to explore. And so each action is associated with a distribution It's unknown to the agent. Nothing is known about the distribution, so they get a sample from the distribution. In this case, a reward R1. They try another action and they get a sample from that R2. And this goes forward. The agent would like to quickly hone in, figure out which is the arm that gives them the highest reward or the highest mean reward in particular. But they have to always take into account the possibility that some other arm they haven't explored yet has even higher reward. So you need to balance those two things. And as I hope you all know, there are algorithms that do this in a very effective way. So upper confidence bound is a classical algorithm that forms a confidence interval, in fact, for the mean reward, using usually large deviation ideas. And it takes the upper bound of the confidence interval, and it takes the largest upper confidence bound to determine which action to select next. It's a beautiful idea. It has got two components in one idea. The upper confidence bound will be large if, for example, the entire distribution is shifted up and to the right. That means that you're getting high reward out of that distribution, so you should sample it for the exploitation reason. But also you could have a high upper confidence bound because you're quite uncertain about that reward. They have a very big interval, and so you should sample the arm for the exploration reason. You put the two together, and you can prove that this algorithm will have logarithmic regret, meaning that it will converge relative to an expert who knew an oracle who knew the optimal arm a priori. You will converge relative to that at rate logarithmic. Your regret will scale as logarithmic in the number of trials. Okay, so on the matching market side, I even have to give less background. This is Gale Shapley and so on. No transactions, just simply matching. So the buyers are assumed on one side of the market to have preferences on the sellers on the other side, and vice versa. And as you all know, there are algorithms that are polynomial timed that converge to a stable allocation of buyers to suppliers, and vice versa. All right, and so the problem we're going to face is, what if you don't know the preferences a priori? You just simply observe noisy utilities, and you're doing exploitation. Can you still have a good regret bound? So just to be clear, our criterion of merit here is a regret bound, and I'll tell you precisely what that regret is. And so in that sense, it's different from some of the other work that's brought together bandits with matching markets or competing agents in general. All right, so our model is going to be, if you have more than one agent, that they are going to choose arms according to maybe their own UCB intervals, but at some point they're going to conflict. And because we're modeling scarcity, we assume that when they conflict, that only one of them is going to get the reward and the other one gets no reward. It's not actually a zero, it's just no reward. All right, so the human, and who gets the reward? Well, the arm has preferences back on the other side of the market, and the arm may be also learning its own preferences. In any case, the human looks at this situation, they say, I really like arm 2, but I see that when I pick arm 2, the bear also is picking arm 2, and when the bear and me both pick arm 2 seems to prefer the bear. Okay, so I better hedge my bets and pick some of the other arms more than I otherwise would to ensure that I come up with a reasonable arm. All right, and so in that language, you can see that I'm going to have presumably have a worse regret here because I'm picking arms more than I otherwise would. And the question is, how much worse is the regret going to be? Well, we have to first of all define a bandit market, and it's just what I've already said. You have the two-way market, and they're all the agents in the market are learning with a bandit algorithm. And then the key is really, we have to have the right notion of regret. All right, so what we've done is define the reward of a stable match. All right, meaning that suppose you knew the mean rewards a priori, and you ran Gale Shapley on those, and the oracle knows that. All right, and so now what is our regret relative to that oracle? Okay, so we picked a certain oracle. Okay, so we call this the stable match, and this is called the stable. We call this the stable regret. Sorry. All right, and so to get upper bounds on the performances algorithm, we also have lower bounds, but to get upper bounds, we define a specific algorithm. So we call this particular algorithm we analyzed the Gale Shapley upper confidence bound algorithm, and it's a centralized algorithm. So in this case, each agent maintains a confidence bound on each action, and they send the upper confidence bound to Gale Shapley, who uses that instead of the preferences to do the matching. Then Gale Shapley sends those back to the agents, and they select the arm according to that recommendation. they get a reward, and then they update their confidence bounds, and the algorithm iterates. Right, so that's a specific algorithm. We've analyzed other algorithms, but that's a specific concrete algorithm. And we're able to prove a regret bound for that. So that's the key here. And I encourage you to look at the proof to see how the game theory and the learning theory ideas come together. Long story short, the regret is still logarithmic in the number of trials. So you actually don't learn any slower than a single agent all by itself in that sense. But there is a constant delta squared in the denominator, which is a average reward gap between the agents. We're used to seeing reward gaps within a single agent. Here we're seeing it between agents. So in particular, if me and the bear are both interested in a particular arm because we have high reward for that arm, that makes delta a small number. And that small number is a constant, but it nonetheless boosts the, it makes the regret worse, okay? All right, now the last bullet there on the slide, it makes a game theoretic statement. It turns out that this algorithm is actually incentive compatible in a certain sense. If everyone else is running the GS-UCB algorithm, then no single agent has an incentive to deviate from that method. Okay, so this, I could go on. We've done other versions of this. We've done a decentralized version of this, which is more delicate. The regret is not quite as favorable. To me, most interesting thing to be doing from here out is to do the recommendation version of this, where we have large numbers of agents and large numbers of arms, and they maybe form a block model of some kind. So you have to first position yourself relative to the other agents. Which agents do I trust? And then use their experiences to guide your own. So you could literally average confidence intervals, or maybe use something like a Thompson sampler to build a hierarchy between the agents. So we're actively working on that. I'll mention a couple of other projects, probably with less time devoted each. This one is on strategic classification with Tiana Zernich and Eric Mazumdar at Berkeley. So classification, again, is a learning idea, and strategic is obviously a game theoretic idea. So we've got predictive models being deployed in social settings. So we can make these predictive models as good as possible, but people will game them, obviously. And my favorite example is the Uber drivers who turned off their cell phones to allow prices to be driven up, and then turned all their cell phones, 30 minutes later and got a higher price. Here, as this is Goodhart's law. If you measure something like poverty index, after 10 years go by, the number of people, more than half of the people have a high value, or in this case, a low value of the poverty index. And then my favorite one is that, having spent a year in Italy, is the one on the right, where, if you're trying to make your insurance rates go down, you want to show that the company that you're exercising. You can do that by putting your cell phone in a device that moves the cell phone back and forth all day long. Okay, so how do you set this up as a learning meets game theory problem? Well, you have a decision maker who's trying to deploy a model, for example, a credit risk model of some kind. They're going to publish that model. Its covariance will be known, and it's going to be used to make predictions about a set of strategic agents. The population sees that, and they realize that they would like to have a higher value than they would normally get with their current covariate X. So they send instead an X prime value to the central decision maker and bias the data the decision maker is receiving to give themselves a larger value. How do you build a system that overall still has high social welfare in the face of that kind of strategic decision making? There have been papers on this, some very good papers modeling this basically as a Stackelberg game. So we have the decision maker updating a model, and we have the agents responding to that model, and this iterates over time. You can show that it has certain equilibria, and it's one where it turns out the decision maker is the leader in the Stackelberg sense, and the population is the follower. We have analyzed this further and realized that there was a degree of freedom missing in these analyses, which is that because you have dynamical systems being used here to track the model and to track the decisions, the rate at which the dynamical systems evolve is another degree of freedom. So the decision maker can decide to update the model frequently, or can decide to update the model more slowly. That is a choice. And it turns out you get different Stackelberg equilibria in these two cases. So we define decision makers being proactive is if they update their model slower than the population. They let the population then do a best response to the model, and then they continue on. So that is one particular Stackelberg game. A different one is where the decision maker updates their model faster than the population. They update very, very quickly, and so they're doing best response instead of the population. All right, so here's a little picture depicting this. This is the proactive case where you can see there's a period of time in which the decision maker is using theta naught as their parameter. And then after an epoch has gone by of t time steps, they adjust it to theta 1, whereas the population of strategic agents is changing their decision more rapidly. So that's the proactive case. We're able to prove a theorem that says that under natural zero regret learning or no regret learning dynamics, which I'll mention more about in a minute here, it turns out the proactive case converges to a Stackelberg equilibrium, and it's one where the decision maker leads. All right. On the other hand, if you look at the reactive case, you also will converge to a Stackelberg equilibrium, but it's a different equilibrium, and it turns out to be one in which the strategic agents lead. That's the reactive case. All right. Now, interestingly, it turns out that there are social implications of this choice. Prior work has shown that, in fact, that a Stackelberg equilibrium from the point of view of the decision maker can have a high social burden. People that truly deserve a positive prediction because they're like good credit risk may have to pay a high cost to get the prediction that they actually deserve. Okay, so it turns out we were able to prove a theorem that if the decision maker in a particular set of statistical models, generalized linear models, if it turns out that you do the proactive case, that both the decision maker and the agents prefer that equilibrium to the decision maker's equilibrium. So just briefly, this is the little experimental setup. We've kind of, to demonstrate this, it's a theorem, but we've demonstrated it here. It's a logistic regression where the agents who are a 0 are strategic. These are the people that are bad risks and they're being strategic. And we assume here that people whose true label is a 1 are not being strategic. We have a logistic regression Bernoulli model, and here is the kind of the penalty that you pay to adjust your covariate down at the bottom. It's a quadratic penalty. All right, so here is the picture just to kind of give a flavor of this. The left plot is the decision maker's risk. The right plot is the agent's risk. If the decision maker is leading, that's one of the red curves. If the agents are leading, on the other hand, that's the blue curve. We're trying to minimize risks. So it turns out that in both cases, actually having the agents lead gives lower, is a Stackelberg equilibrium with lower risk for both the decision maker and for the agents, right? So that's the content of this picture. All right, so both players prefer when the order of play is flipped. All right, so long story short, there are Stackelberg equilibria here, but there are many of them, and some of them are preferable from the point of view of agents and decision makers, and you can get control over that by having the dynamics be responsive to which you want to choose. All right, so even less time devoted to the next two, which I'll very quickly allude to. This is a topic that several other speakers know more about than me and have been working on, but these are optimal Meyerson-style auctions. We're looking at robustness. So this is with Winchwogo and Manolis Zampatakis, who are working with me at Berkeley. Again, this is an auction setting. You all have, know this well. The question is, if we're not assuming we know the value distribution a priori, if we're just learning from, say, even a single sample, can we plug that in and still get a good auction that has maybe revenue maximization? And the answer is yes, you can, but robustness really becomes a problem here. If you get bad data, or if there's some adversary, you can actually change the answers quite severely. So we want to make sure we don't have a lack of robustness in this critically in this setting. So we're able to show we have designed what we call a robust empirical Meyerson auction, which I'll briefly allude to on the next slide, that turns out to be robust to any distribution within alpha of the true distribution in the Kolmogorov-Smirnov distance sense. This is the right distance to choose here because it allows arbitrary corruptions of data, and so you can have alpha of your data points completely moved and still be robust. So we showed that you achieve revenue within a factor of 1 minus O of alpha under this setting. and turns out that meets a lower bound as well. It applies to the multi-bidder setting under more assumptions, in particular monotone hazard rates and regular distributions. Let me not get into details here, but basically there are true evaluation distributions and there are corrupted values that stay within Kolmogorov KS distance of alpha I after the corruption. And here's the theorem that you can prove. You can show that the revenue is within a factor of 1 minus O of alpha in the monotone hazard rate case, and 1 minus the square root of the sum of the alphas in the regular case. And there's a sample complexity bound there at the bottom. The algorithm sketch, just to give it briefly, is that you're using a particular lower convex envelope of a piecewise constant function using link functions. And so you basically, once you've kind of patched up the empirical distribution in a particular way, you can run the Meyerson auction on this envelope, and that actually is the algorithm. That turns out to be robust. So this paper is just as of last week on the archive if you're curious to see details. And then lastly, a 2-minute version of a new project that just started this year with 4 colleagues at Berkeley. We're back to matching markets here and bandit feedback, but we're going to be interested not just in the regret, but in the actual equilibrium that results, and we're going to allow transactions to achieve equilibrium that we'd like to achieve. And so again, we're trying to learn stable market outcomes under uncertainty. We're going to allow transferable utilities in this case, so we're more in the Shapley-Shubik setting. And we've introduced a novel measure of instability, and the payments that we offer are the minimum, the definition of it is that it's the minimum amount the platform could subsidize to an agent to achieve this notion of stability. And the learning side then, if you take that stability measure as a loss function, we're able to design low regret algorithms that are actually able to learn these matchings. All right. So again, this paper actually is still being prepared, so it'll be in the archive within a week, but it is just being finished. All right, so let me just finish by returning to this slide. Again, machine learning is kind of the point of departure of this. Statistics meets computation, and sort of bringing in economics ideas to ensure that the kind of learning we do is actually informed by economic principles. Again, I believe this is just becoming a hugely important, high stakes area to be working in. And I want to leave this last slide up as I finish. I just philosophically feel compelled to say something about machine learning AI. It's become the buzzword on all tongues everywhere. I don't think it's particularly good language. I don't think this is about artificial intelligence. It's about algorithms and statistics and incentives and so on. All right, but what is the phenomenon of the era, I think? Actually, I think it's very much like chemical engineering in the 40s or 50s. Before the 40s or 50s, you had chemistry and fluid mechanics and quantum mechanics and so on. So you could envisage putting together, making new products in the laboratory. But then to build factories and do this at huge scale that had, economic value, it actually worked. New thermodynamics were needed, new principles were needed, and that developed into a field called chemical engineering, which has had a huge impact on our world. Similarly, electrical engineering, same kind of story applies 50 years before. I think what we're seeing now is an explosion of practical applications of mathematical ideas from the last century in economics, statistics, and computer science being brought together to build real world systems at really planetary scale in commerce, in health, in finance, you name it, any area of human livelihood is being informed by all of these sides, computation, statistics, and economics. If we're going to use terms like AI and machine learning, I think we have to take seriously this notion of engineering and real world systems that we are trying to build that are solid. And I will finish with that. I will finish.